I'm happy to see you guys all here today. And today it's a very big day for us. We're going to show you today the update that we were preparing quite a long time. Firstly, as our as our any update, we add some new resources, XOR keys, new NAND chips, and ECC code words for most modern for new chips that we didn't see before. So you got new resources, you got new pinouts. It's all available in updated databases. To get new pinouts, you basically don't have to do anything for the new resources. You need to download database files from your client portal and update it. So then you're going to get these new resources. The first thing I wanted to tell you about, it's improvement of our file assembler. I'd like to remind you that file assembler is a tool in our software that can assemble pictures and videos and documents, doc files, based on some intelligent algorithms. It's not just carving, which is looking for header and footer of files, and then it decides that, all right, this is the file. But it scans whole surface, whole capacity of the device, and then is trying to analyze the content of that pieces of files, and then put the pieces together. So it's like it works like a puzzle assembler. It's looking for pictures, and for example, like it's shown here, there is one lady is here. That's the beginning of the picture, and somewhere else assembler may find the end of this picture, and then it will just put these two parts together, and the picture will be recovered. So it works for fragmented pictures, fragmented video files, and document files. And yes, it's very good, it's intelligent, but there is one problem with the NAND data recovery. The thing is that NAND devices may have, even after bit error correction, bit errors may still be there. And let's see how picture looks like when there is a bit error in the picture. We can see that the picture is not fragmented. It's not fragmented, but because of bit error, we can see that the color is changed from some point. And then, since assembler is analyzing what is shown on the picture, assembler will think that basically picture ends somewhere at this point, and then new picture begins. So assembler will was thinking that this is a fragmented picture, and if you have a case with many bit errors, so then you may see time of analysis may increase, and because assembler will try to find end of this picture, but it will never be succeeded because the end of the picture is here, and yes, it will keep looking. It will spend time for this, and finally it will say that, okay, this picture is unrecoverable, and that's it. So picture will not be recovered, but time will be spent for nothing. So what we decided to do, we added bit error detection for this algorithm, the same like we used for our regular carver. Our regular carver, I'd like to remind you, can search for pictures, and it can detect bit errors. It can detect either picture is totally good, no problems there, or picture may have bit errors. So now assembler can do this too. And as a result, we have this. Before, it's the same case. So before we had like unrecoverable more than 1,000 pictures, and unfragmented pictures, it was like 3,500. New algorithm detected, well, firstly, we added some other pictures for detection. So now it can find more pictures. And secondly, it quite quickly, it detected 900 pictures with bit errors. So these pictures will not be analyzed, and assembler will not try to look for parts of that pictures. And yes, in this case, in first case, analysis may go quite a really long time. Now it may be much faster. It all depends on number of pictures on your device and the number of bit errors. So that's improvement of the file assembler. And the next thing, it's the main thing of this update. It's a database of solution. As we wrote in our news, within years we were trying to do the best tool for data recovery from NAND devices, for research of algorithms, and so on and so on. So if you want to do some research, reverse engineering of some device, I'm quite sure that VNR is the best solution. It has a lot of tools to analyze, to find some things, resources, unsupported devices, from unsupported devices, and so on and so on. But apparently, some people wanted to not do research, but to just apply solutions and get money, right? So, but you know, database of solutions was quite not the best idea to do, because you know that there are hundreds, thousands of different devices, and to make a good database, you have to do the database with a huge number of solutions that will cover all of that devices. So we were concentrated to do the tool that will cover like any number of any device. But then we came with an idea to do the database which will be adjustable, which will have kind of flexible solutions. And now I'm going to tell you how we implemented this. So the main things of our database, it's firstly, it's integrated into VNR, so you don't have to go to some website or internet somewhere. It will be automatically, it will be in the VNR, straight in VNR. It's dynamically updated. So this all the solutions will be uploaded from our side, and you will not have to wait for updates and so on and so on. It will be updated each time when you run the VNR. The database is a local, so it will be kept on your computer. But as I told you, on each start of VNR, it will be updated from the cloud. And the last thing, it's solutions. They are adjustable automatically. Of course, you can adjust them, and another thing that could be adjusted automatically. And I'll show you now how it works. So that's the main window, like the first window you're gonna see when you start the case. And here you need to select type of device you're dealing with. If you select some monolithic device, you can select it by picture. If you, here, if you selected some monolithic device, then you will be, it will be necessary to select the device by pictures, because in case of monolithic devices, you don't know what controller precisely will be in the inside. But if you are dealing with normal, let's say standard device, when you have separate chips for controller and NAND memory, then you will be asked to, okay, there is no that picture, but later we'll see, you will be asked for selecting the controller, vendor of controller, and controller model. Then the task will be started as usually, and you will be asked to select configuration for the NAND memory. So the VNR will get to know NAND memory ID, and on the previous step you selected controller. So now the VNR knows this combination, NAND memory and plus controller. And if there is a solution for this combination, controller and NAND memory, when you will start to read the chip, instead of getting just one physical image like you got before, the utility will say that there is a solution and if you want to apply it. And once you click on apply, you're gonna get the full chain here already on the workspace. So before you got just physical image and then you had to perform all that, you will have to search for ECC, XOR, and so on and so on. Now it all will be brought automatically to the workspace, and then you will have to read the chip, and basically that's it. If you have full match, like number of crystals, number of chips, controller, and memory ID, then so basically if you got the very exactly same device like we had and we added solution for that device in the database, then you will need just to read the chip, fix bit errors, and get the data. But as I told you, number of those devices is huge, and we may have device with one memory chip. You may have same device, but with a bigger number of memory chips. And in that cases, like this approach will not work. I mean, when you have exact solutions. So what we did, we made 3 types of solutions. The first one is the full solution, where as I just showed you before, when you have a full match of the controller, NAND ID, number of chips, and crystals. In that case, you will get the full solution. If, let's say, we got some device with 1 memory chip, and then you got with 4 memory chips, then the database will offer you partial solution. So it will look like, yeah, that's the full solution. And the partial solution will look like this. So you're gonna get, for the most of parameters will be defined, markers table will be mostly set up. You will need to read the memory chips and then to unite these chains from all the chips, because we can't know in advance how we need to unite them, either by pages or by dumps or somehow else. If we will get the same device with 4 memory chips, then of course we will unite them and you're gonna get the full solution. But in case if we didn't get that before and we get just with the 1 chain, 1 chip, let's say, or with 2 chips, and you got it with 4 chips, so it will be automatically adjusted for your specific case. You will need just to unite this for chains, for chips or for crystals. And it's quite simple. There are articles how to unite that, webinars. So that's easy. It's just, 5 minutes of work, usually. Well, sometimes uniting could be quite complex, but in many cases, it's pretty simple. Okay, so that was first 2 types of solutions when we have the match of combination controller and NAND ID. Here we have controller and NAND ID plus number of chips and crystals. In this case, we have much of only controller and NAND ID. And of course, sometimes we may not have this combination in the database. So for that cases, we made kind of controller templates that will look like this. So we know that this controller, for example, you selected a controller, I don't know, some Phison controller. And we know that that controller normally use firstly ECC, then XOR, then maybe pair, and then marker stable. And with a quite big chance, in your example, it will be the same. So all you will have to do, you will need to search for ECC, like automatically, you know, you have ECC element here already, so it works like a hint. So you see, okay, ECC, I need to find ECC, and it's very simple. As I told you before, we made a lot of tools for analysis, and like to find ECC, it's pretty simple with ECC support. So all you need to do, you need just to click on find ECC, and you're gonna get the result. The same for XOR. You run XOR analyzer, you will get a XOR key, and right, it will be done. Marker stable will be more or less prepared to, like marker stable will be either prepared, or you will see some tips for marker stable, like header is that byte, LBN is those 2 bytes, and you will need to do this and that. So the controller template, it's like a hint, like a suggestion, how to proceed with this controller, how to do, or what steps you need to do with this controller. And that's the third type of the solution. Of course, we are going to get as much as possible number of full solutions. So we want to avoid you guys from research. So we want that you just apply the solutions, and that's it, get the data. And the number of full solution will be growing day by day. But even if we don't have the necessary solution for your specific device, I hope that partial solutions or controller templates will help you to solve your cases. And now, guys, I want to show you several examples how it works, how the database works. So I got here the VNR, and let me create new case like this, next. And as I told you, here you need to select the type of your device. There are such devices for now. Maybe we will add some new ones. We'll see how it will be growing. So in my case, I have a typical classic UFD device. So I select this, and then I need to pick the vendor of controller. So in my case, it's Phison. And then this model, very typical, very standard Phison controller. And then finish. So at this point, we are having the reader, and we need to select the configuration firstly. Before we had just one button for reading memory chips and selecting configuration at one time. Now we split these functions in 2 buttons and 2 steps. So firstly, we click on this button, set configuration, and the VNR is reading the ID. And now, so that's the ID we have and configuration for this chip. Now I click to apply configuration, and the VNR offers me to check reading. We always suggest to check reading before to read the chip, actually, because, you know, something may be bad with the connection or with configuration. Maybe you need to decrease voltage or something else. So it's better to firstly have a look into the chip and check if everything more or less good there. If you see normal patterns, know some artifacts, and so on. So basically, we can see here a normal bitmap with a straight pattern, service area, and so on. So it looks good now. It looks good. And now we can start reading. So I will click to read memory chips. And in this step, I need to select number of memory chips. So in my case, in my example, it was one memory chip. So I keep this number. I don't change it. Okay, and I got such a message. There is a solution. Apply, cancel. Okay, let me try to apply it. And yes, that's the solution here. And now if I will click to OK, it will start to read the chip. I'm not going to do this to save our time. So I will click on cancel, and I have the memory chip. I mean, I have the dump already prepared. So I will just select it here. So here I got dumps, and that's the first dump I want to work with. So we got the dump and ECC map. Well, I better will enable it, and ZOR, ECC, pair is all here. I have some tip hint here that I need to use page filter for the first blocks in the file system, because first blocks are written in SLC mode. So some pages should be skipped, some not. And yeah, I'll show you now how to do this, because, you know, number of those SLC blocks may be different on your device. In my case, it's like, let's say 10. In your case, it could be another value. And what is SLC blocks, how to apply this page filter. We also have some articles, and maybe I think we will add here a link to that article, so you will better see how to proceed with this page filter. So for now, we need to click on create table. And when you open the table, it's all already arranged. And yes, it's all here. And there is information about page filter. So page filter, it's this column. And let me show you more. Okay, I think I will disable ECC for now. So this is how SLC blocks look like. Okay, so you can see that one page is there is one page with data, and then several pages with data, several pages with FFs, and those FF pages should be filtered. And to do this, I will use this page filter. If let me do it like this. So after XOR and all that preparations, SLC blocks look like this. So I can see that this block looks like SLC, so I check the page filter here. You know, usually SLC blocks go in row until some point, until some block. And even if there are some blocks that do not like SLC, they are still SLC, because after we have something like this, where we can see that this is SLC block. So we have like 4 pages here with data, then 2 pages FFs. So without data, that should be just skipped, and so on until the end. So I will keep checking these blocks until I'll see normal data. Oh, and you see from this block, the bitmap looks like normal data. Yes. So this block should be unchecked, and page filter will be applied from block 0 and until block 17 in hex. And that's it. That's all you need to do. Now you just, and I want that you understand it's not possible to apply this page filter automatically because a number of SLC blocks could be different. So it's, yeah, you need to do this by yourself. Maybe in your case, you will not see any SLC blocks. Then you will just skip this step. But if it will be necessary, the page filter is already prepared and you just need to click on that checkboxes. That's it. So now I enable ECC correction, and yes, the data is here. So that's how full solution works like. Now let's have a look into a partial solution. Okay, new case. Okay, let's say we have the same controller. Same controller, but now we have another NAND ID. So instead of this NAND ID, we have another one. Apply configuration. I will not check reading because I still have the old chip. I just selected another configuration, so I will not try to read it. I just click on cancel. And let's say I have one memory chip, and it says me that there is a solution for this chip. If I click on apply, I'm going to get the full solution here. But let's imagine that in your case, you have not one chip, but you have two chips. And we didn't have two chips. We didn't have the device with two chips. So you click on OK, and there is a message here. There is a partial solution. Do you want to apply it? Yes, you do. And now it offers you to read the chips. So you're going to get something like this. OK, so to proceed, I will need to select physical, select dumps for these chips. So it's here, first dump and second dump. Okay, let me check ECC. Yes, it seems to be compatible. So we have two dumps. We have a list of preparation here. And to proceed, I need to unite these two chains. To do this, I have two options how to unite it, either by two pages, because I have a pair here, or by dumps, in case of by two pages if data was written simultaneously into two chips, or by dumps if data was written in one chip firstly and then in another chip. More information about this you can find on our webinars, on our YouTube channel. I think that we will have to add some link here to that webinar. So to understand how data was written, I need to open two dumps and check patterns. If I will see same patterns or similar patterns, that means that same data was written simultaneously into two chips. And basically that's what we see in this case. Similar data with the same lines, like here, for example, you see it's very typical. So, okay, within 15 seconds, I can see that I need to unite these two chains by 2 pages, and this is actually the default way of uniting. So here area size has the size of 2 pages. One page is 8 kilobytes approximately, so 2 pages will be 16 kilobytes approximately. And then I unite it like this, create table, and there is a default list of commands. Do this better with ECC on. Default list of preparations in markers table, which will be most probably compatible with your case, but you need to recheck it. So as you can see, you have LBN already, and it's all arranged. Starts from 0, so you need to, well, yeah, what an ideal case. I just checked LBN chain, and I can see that no errors found. So this case is compatible. This solution is compatible with this case, appears to be compatible. All you need to do, you had to do just to unite these two chains. Now I click to create logical image, and it should be fine now. File system is empty, probably it's formatted device, but we can see that it works. So that's how partial solutions work like. And now the last case, when, and I'd like to remind you that partial solution you're gonna get if you have the combination of NAND memory and controller, same like we had or somebody had and added to the database. Only number of chips is different. You will need to unite it. Close case, and now the new case. And new case gonna be about controller template. Again, same controller, but in last case, let's say that we didn't have this combination of memory ID and controller. So the ID now is different. Apply configuration. I will not check reading again because I still have the first chip. And yes, read memory chips, one memory chip. And now it's saying me that there is a controller template. Do you want to apply it? Yes, and this is how it looks like. That's the controller template. So the difference here is that you still have elements that most probably should be here. Like from our experience, we know that this controller uses such transformations in this order. And you will need, of course, firstly read the chip. I will not do this. I will just select it here. And then you will need to find the ECC and XOR for this specific case. So to do this, firstly on ECC, I click on Find ECC, select Files and Controller, find Okay, and ECC is found. So that's the ECC, select, add data as yes, add, and we can see that ECC is fine. Now the XOR. For now, XOR here works like like a hint. You understand that, okay, and that place should be XOR element. So to find the XOR is the best way for now. The best way is to click on ECC and run XOR analyzer, because on the XOR element you can select XOR key manually only if you open, if you click on this button, and you will have to select it manually. If you want to find it automatically, now you need to select ECC and run XOR analyzer. Later, I think that XOR analyzer will be available on XOR element 2. So I click on XOR analyzer. How to work with XOR analyzer? We have some videos too, so you can easily learn this subject by yourself. So actually I can try to validate key even on this block and just select the one with the highest result and highlight it. So this one seems to be the good XOR key. I don't have here 99% because of these fat tables, but I can see that XOR key works totally fine, because from the start of block to the end of block, I don't see any noise. So I can see that all the data is descrambled. So this key could be selected. If I will try to run validate key on this block, for example, then I'm gonna get 99%, the same key. Anyways, I click on apply XOR. I put it here. This one could be deleted and connected like this. Okay, now I will click on create table. Again, markers table has parameters here that most probably will be fine for this controller, but you will need to recheck it. Okay, so, well, you see, that's why you need to recheck it. The chain here is actually going until 12F3, but this block is checked too, and it looks like kind of out of range, probably. Yes, so I think that it's better to just uncheck it and then create logical image. Enable ECC and then file system viewer. And again, data is here. So this is how controller template works. In this case, you will get kind of a skeleton of solution, and you will need with the elements which will be which you will have to use for this case, and all you will have to do just to select parameters for those elements. Okay, and the last thing I was going to show you, it's you know, nowadays we have a lot of monolithic devices. So in case of monolithic device, it's going to be like this. Let's say you got some micro SD card. I got here a micro SD card. It's a SanDisk. I don't know if you can see it. It's 128 gigabytes. So I put it into this adapter, which is made for SanDisk micro SD cards. That's the name, micro SD 3x7 pods. And yeah, micro SD next. And in case of monolithic devices, you can't select the controller because you don't know what controller you have there. You need to select a vendor of the device. It's a SanDisk. As I told you, we just started to fill the database. So now it's just 3 devices here. It's going to be much, I mean, 3 micro SD card of SanDisk devices. Later, of course, it will be much, number of these devices will be much bigger. And you will need to select the device by the picture. In case of not fake devices like SanDisk and so on, there is a good chance that a controller and algorithm of different devices with the same design will be the same. So there is a good chance that if you select this device and the NAND memory will be the same like we had, the solution will work for you. If you will do double click, you can see some pictures from this device, like top side, back side, and you can compare, you can make sure that you have exactly same device. So you select it, click on finish. And reader is here. Okay, so now you need to select configuration as usually. Configuration is here, apply, check reading. Okay, let's check reading. Okay, data seems to be readable, seems to be fine. And now I should read 120 gigabytes. Okay, no, I'm not going to do this. I'll just fix ECC errors. Okay, this is quite a complex solution. So there is quite a big instruction here how to proceed with this device. In your case, you will have to adjust it a little bit, and there are some instructions here how to do this. So firstly, let me select the dump. It's here. Now let me check the map. So ECC is good. And now there are 2 markers table. The first markers table works to filter blocks with data only, because the device is quite big, and you know, building markers table may take pretty much time, because in this case, it's necessary to assemble logical image not even by pages, but 1/4 by quarters of pages. So there could be millions of that chunks that should be assembled. And if you have like device 128 gigabytes and there are just several gigabytes of data, if you will take the blocks with data only, the assembling of logical image will be much faster than to assemble 128 gigabytes. So to save the time, we use here 2 markers table. The first markers table is made to take the blocks with data only. And you understand that in each case, it will be number of blocks will be different. Even very same devices. So one user may have 10 gigabytes of data, another one may have 100 gigabytes. So that's why you need to adjust the second markers table for that precise amount of data. And here you have the instruction how to do this. I'm not going to create table for these 2 devices because each table has several gigabytes of data, so it's much faster just to upload it, and even uploading may take some time. in case of markers table 1. Okay, so this one went quite quickly, and this markers table I will upload to. You see it has size 7 gigabytes, 6 gigabytes. All right, finally we got the table. And the last thing would be to create logical image. It will take some time. Okay. It's ready. And the last thing would be, let's hope that it's going to be okay. Yes. So we got some pictures here. And yeah, I can see the pictures. And that's it. That's what we wanted to show you, to introduce you. The next our plans, the very first our plans for the next update would be to create some viewer of solutions, to make possible for you guys to upload solutions, and of course to upload solutions to the database. That's what we are going to do next. Okay, then thank you very much for attending this webinar. Try to use this in case of some questions, suggestions later. Send us emails how we can improve this. And see you soon. Thank you.